There is a moon in our solar system that does not play by the rules. It circles Saturn in the cold darkness, far from the light and warmth of the sun. And when you look at this moon, something feels wrong, not because of its size, not because of where it sits in the sky, but because there is a wall running across its middle that should not exist. This wall stretches for over 1,000 kilometers. It rises so high that it dwarfs every mountain on Earth, and it follows the equator of this small, icy world with a precision that makes no sense. Nothing in the way moons form should create something like this, yet there it is. A ridge so tall and so perfectly placed that scientists still shake their heads when they try to explain it. Before we drift further into the dark rings of Saturn, if you find peace in these cosmic journeys, please leave a like and subscribe to join our sleepy community. Tonight, we are going to explore this strange moon. We are going to walk along the base of a wall made of ice and rock, a wall that towers into a black sky full of distant stars. We are going to ask the questions that scientists have been asking for decades. How did this ridge form? Why does it sit exactly on the equator? And why does this moon, more than any other world we have found, look like it was made by something other than nature? This is the story of Iapetus, the moon with the impossible wall. The mystery that still defies the laws of space. Far from the inner warmth of our solar system, past the rocky worlds and the great gas giant Jupiter, there lies Saturn. This is a world of quiet majesty, wrapped in golden bands of cloud and circled by rings of ice and rock. Saturn is the crown jewel of the outer solar system, and around it, a family of moons drifts through the darkness. Some of these moons are tiny, just chunks of rock and ice that tumble through space. Others are giants in their own right. Titan, the largest of Saturn's moons, is bigger than the planet Mercury. It has a thick atmosphere and lakes of liquid methane on its surface. Enceladus, a smaller moon, shoots geysers of water into space from an ocean hidden beneath its icy shell. But among all these worlds, there is one moon that stands apart. One moon that looks different from every other object we have ever seen. That moon is Iapetus. Iapetus orbits Saturn at a great distance. While most of Saturn's large moons stay close to the planet, circling within the plane of its famous rings, Iapetus wanders far away. It travels at an average distance of over 3.5 million kilometers from Saturn. That is more than twice as far as the next closest major moon. At this great distance, Iapetus is cold. Very, very cold. The surface temperature can drop to nearly -200 degrees Celsius. At these temperatures, ice is as hard as stone. Water does not flow. It sits frozen and still, waiting in the darkness for something to change. The journey from Earth to Iapetus would take years. If you could somehow travel there, you would find yourself in a place of deep silence and endless night. The sun, so bright and warm here on our planet, would appear as nothing more than a very bright star in the black sky. Saturn would hang above you, a giant banded ball glowing with reflected sunlight, and the rings would stretch across the heavens like a thin, bright line. But it is not the darkness or the cold that makes Iapetus special. It is what you would see when you looked at the moon itself. When Giovanni Cassini first spotted Iapetus through his telescope in the year 1671, he noticed something strange. He could see the moon on one side of Saturn, but not on the other. For weeks at a time, Iapetus would appear as a faint point of light. Then it would disappear. Then it would come back again. Cassini was a careful observer. He thought about this puzzle for a long time, and eventually he figured out the answer. Iapetus must have two faces. One side must be bright, reflecting light like fresh snow. The other side must be dark, absorbing light like coal. And because Iapetus always keeps the same face pointed towards Saturn, just as our own moon always shows the same face to Earth, Cassini could only see it clearly when the bright side was turned his way. This was a brilliant insight, and centuries later, when spacecraft finally visited Saturn, they proved that Cassini was right. The difference between the two sides of Iapetus is striking. On one side, the surface is bright and icy. It reflects more than half of the light that hits it, making it almost as reflective as the brightest moons in the solar system. This is the trailing hemisphere, the side that faces backward as Iapetus moves through space. On the other side, everything changes. The leading hemisphere, the side that faces forward as the moon travels along its orbit, is coated in something dark, very dark. This material reflects only a tiny fraction of the light that touches it. If you stood on this side of Iapetus, the ground beneath your feet would be nearly as dark as asphalt on a freshly paved road. The line between these two regions is sharp. There are no gentle fades from light to dark. Instead, the change is sudden, almost as if someone had dipped the moon halfway into a bucket of black paint. Scientists call the dark region Cassini Regio, named after the astronomer who first noticed this strange difference. The bright regions have their own names too. North of the equator lies Roncevaux Terra. South of the equator lies Saragossa Terra. These names come from an old French poem about knights and battles, a fitting choice for a moon that seems to carry the scars of some ancient conflict. For many years, the two-tone appearance of Iapetus was its most famous feature. Scientists puzzled over the dark material. Where did it come from? Was it volcanic ash from eruptions deep inside the moon? Was it dust swept up from space as Iapetus moved along its orbit? Was it something that had always been there, or something that arrived later? The answer, we now believe, involves another moon entirely. Far beyond Iapetus, in the outer reaches of Saturn's gravitational grip, there is a small, dark moon called Phoebe. Phoebe orbits Saturn in the opposite direction from most other moons. It is probably a captured object, a wanderer from the outer solar system that got caught in Saturn's gravity long ago. Phoebe is also very dark, and when meteors slam into its surface, they kick up clouds of dust. This dust drifts inward towards Saturn, creating a vast, thin ring that is nearly invisible to the eye. Iapetus, moving forward through its orbit, sweeps through this ring of dust like a car driving through fog. The dark particles stick to its leading side, coating it over millions of years. But that is only part of the story. Once the leading side of Iapetus became slightly darker than the rest of the moon, something interesting happened. The dark material absorbed more sunlight. This made the surface a little bit warmer, and on a world made mostly of ice, even a small increase in temperature can have big effects. The warmer dark side began to lose its ice, not through melting, because it is far too cold for liquid water. Instead, the ice turned directly into vapor, a process called sublimation. This vapor drifted away from the warm, dark regions and settled on the colder, bright regions. As it landed, it froze again, making the bright side even brighter. This created a feedback loop. The dark side got darker because it was losing ice. The bright side got brighter because it was gaining ice. Over billions of years, this process turned a subtle color difference into the dramatic contrast we see today. One half of Iapetus became as dark as coal. The other half became as white as snow. It is a beautiful example of how small changes can lead to big results over very long periods of time. But the two-tone coloring of Iapetus is not what makes this moon truly strange. That honor belongs to something else entirely, something that was not discovered until the year 2004. On the last day of December, as people on Earth were preparing to celebrate the new year, a spacecraft called Cassini was making its first close pass by Iapetus. This probe had traveled for 7 years across the solar system to reach Saturn. It was named after the same Giovanni Cassini, who had first observed Iapetus more than 300 years earlier. As Cassini approached the moon, its cameras captured images of the surface in detail never seen before. Scientists back on Earth gathered around their screens, eager to see what secrets Iapetus had been hiding. What they saw took their breath away. Running along the equator of Iapetus, stretching for more than 1,000 kilometers, was a massive ridge. A wall of mountains so tall and so precisely placed that it seemed almost impossible. This was not a random chain of peaks scattered across the surface. This was a single, continuous structure that followed the equator with uncanny accuracy. In some places, the ridge rose nearly 20 kilometers above the surrounding plains. To put that in perspective, Mount Everest, the tallest mountain on Earth, stands less than 9 kilometers above sea level. The peaks on Iapetus were more than twice that height. They were among the tallest mountains in the entire solar system, rivaling the great volcanoes of Mars. But the height was not the strangest part. What made scientists truly pause was the shape and placement of this ridge. The wall ran almost exactly along the equator. Not roughly, not approximately, almost perfectly. If you drew a line around Iapetus at its widest point, the ridge would follow that line with only tiny deviations. This kind of precision is extremely rare in nature. Mountain ranges on Earth, like the Rockies or the Andes, curve and twist according to the movement of tectonic plates. They do not follow neat geometric lines. The ridge also had a distinctive shape. Many of the peaks formed sharp triangular profiles, with steep sides meeting at pointed crests. The width at the base varied from 20 to 70 kilometers. The whole structure looked less like a natural mountain range and more like something that had been placed there deliberately. Of course, no one seriously believes that aliens built a wall on Iapetus. But the precision of this feature has forced scientists to come up with some very creative explanations. Before we explore those explanations, let us take a moment to appreciate just how remarkable this ridge really is. Iapetus is a small world. Its diameter is only about 1,470 kilometers. That is roughly 1/3 the size of our own moon. On a body this small, gravity is weak, much weaker than on Earth. An object that weighs 100 pounds here would weigh only about 2 pounds on Iapetus. You might think that weak gravity would make it easier for tall mountains to exist. And in some ways, that is true. On Earth, the weight of rock pressing down from above puts a limit on how tall mountains can grow. If you try to build a mountain too high, the rock at the bottom would crush and flow outward. The mountain would collapse under its own weight. With weaker gravity, this limit is higher. Mountains can grow taller before they start to buckle and spread. This is why Mars, with its lower gravity, can support Olympus Mons, a shield volcano that towers nearly 22 kilometers above the surrounding plains. But there is more to the story than just gravity. Iapetus is made mostly of ice, water ice to be specific, and ice behaves differently from rock. Under pressure, ice can flow slowly over time, almost like very thick honey. This is how glaciers move on Earth. The weight of the ice above pushes the ice below, causing it to creep forward inch by inch. On Iapetus, the ice is so cold that it is much more rigid than the ice we know. But over billions of years, even cold ice can shift and settle. A tall mountain made of ice should slowly slump under its own weight. The peaks should round off. The steep slopes should gradually flatten. Yet the ridge on Iapetus has remained sharp. Its slopes are steep. Its peaks are pointed. This suggests that whatever built it to last. The structure has stayed intact for billions of years, resisting the slow creep of ice and the bombardment of meteors from space. Speaking of meteors, the ridge is covered in craters. Small impacts have pocked its surface over the eons, leaving circular scars that tell us about the age of this feature. By counting these craters and comparing them to crater counts on other parts of Iapetus, scientists can estimate how old the ridge is. The answer is humbling. The ridge is ancient, almost as old as Iapetus itself. Whatever created it happened very early in the history of the solar system, when Saturn's moons were still young and the debris from planetary formation was still flying through space. This timing creates a puzzle. Most geological features that we see on moons and planets formed through processes that took a long time. Volcanic eruptions over millions of years. Tectonic stress building up and releasing. Slow shifts in the crust as a world cooled and contracted. These processes can create mountains and valleys, but they usually leave behind features that are jumbled and irregular. The ridge on Iapetus is neither jumbled nor irregular. It is precise. It is aligned. It looks like it was made all at once, in a single event that shaped the entire equatorial region of the Moon. So what could have done this? Scientists have proposed many ideas over the years. Some of these ideas focus on forces from inside the Moon. Others look to events that happened outside, in the space around Iapetus. Each theory has its strengths and weaknesses. Each explains some parts of the mystery, while leaving other parts unanswered. Let us explore these theories together. Let us walk through the possibilities and see what they tell us about this impossible wall. The first category of explanations focuses on internal forces. These are called endogenic models, from a Greek word meaning born inside. The basic idea is that something happening deep within Iapetus pushed the ridge up from below. One version of this idea involves the way Iapetus spins. When Iapetus was young, it probably rotated much faster than it does today. Back then, it might have completed one spin every 16 or 17 hours. At that speed, the Moon would have bulged outward at its equator, just as Earth bulges slightly at its equator due to our planet's rotation. This bulge happens because spinning creates an outward force. You can feel this force if you ride a merry-go-round. The faster it spins, the more you feel pulled toward the edge. On a spinning planet or moon, this force pushes material outward at the equator, making the middle wider than the poles. Over time, Saturn's gravity slowed Iapetus down. The massive planet exerts a tidal pull on its moons, and this pull acts like a brake, gradually reducing their spin. Today, Iapetus takes about 79 days to complete one rotation. It is tidally locked to Saturn, meaning it always keeps the same face pointed toward the planet. As Iapetus slowed down, its bulge should have relaxed. The material that had been pushed outward should have settled back, returning the Moon to a more spherical shape. But if Iapetus cooled and froze quickly enough, the bulge might have gotten stuck. The outer shell might have hardened before the interior could adjust. This could explain why Iapetus has an unusual shape. Even today, the Moon is slightly flattened at the poles and wider at the equator than it should be for its current slow rotation. It looks like a frozen snapshot of a faster spinning past. But does this explain the ridge? Some scientists thought that as Iapetus despun and its shape tried to adjust, stress might have built up along the equator. This stress could have caused the crust to buckle and fold, pushing up a ridge of material. It would be similar to the way two cars crumpling together in a slow collision create a raised edge where they meet. The problem is that this model does not quite fit the evidence. Other moons that have experienced similar slowdowns, like Europa orbiting Jupiter, have tectonic features scattered across their surfaces. They have cracks and ridges in many places, not just along the equator. If despinning caused the ridge on Iapetus, we would expect to see similar features elsewhere on the Moon. But the ridge is unique. Nothing else like it exists anywhere on the surface. There is also the question of timing. For the despinning model to work, Iapetus would have needed to freeze very quickly, trapping the stress before it could dissipate. But the Moon would also have needed to stay warm enough for the crust to buckle and deform. These two requirements pull in opposite directions. It is hard to find a scenario where both are satisfied. Another internal model involves convection. Deep inside some moons and planets, hot material rises while cooler material sinks, creating slow churning motions within the interior. This convection can push against the crust from below, creating surface features. On Earth, convection in the mantle drives plate tectonics. The continents drift, mountains rise where plates collide, ocean basins open where plates pull apart. The surface is constantly being reshaped by forces from below. Could something similar have happened on Iapetus? The answer is probably not. Iapetus is small and cold. Its interior likely froze solid very early in its history. Without a heat source to keep the interior warm, there would be no convection. And even if convection did occur for a brief time, it would not naturally produce a ridge that follows the equator so precisely. Convection patterns tend to be complex and irregular. They would create bumps and depressions scattered across the surface, not a single linear feature. A third internal model suggests that the ridge formed when Iapetus contracted as it cooled. As the interior froze and solidified, the Moon would have shrunk slightly. This shrinking would have put the outer shell under compression, squeezing it from all sides. When you squeeze a hollow ball, the surface can buckle and wrinkle. On Iapetus, this compression might have focused along the equator for some reason, pushing up a ridge of material. But once again, the precision of the ridge is hard to explain. Why would compression create a feature that follows the equator so exactly? And why would it only affect one region of the Moon? The ridge is mostly confined to the dark hemisphere. If compression was the cause, we would expect to see similar features all around the Moon, not just in one area. All of these internal models share the same basic problem. They can explain how some kind of ridge might form, but they struggle to explain why this particular ridge follows the equator with such uncanny precision. They also have trouble explaining why Iapetus is the only moon in the solar system with a feature like this. If internal forces were responsible, we might expect to see similar ridges on other small icy moons, but we do not. This has led many scientists to look outward for answers. If the ridge did not come from inside Iapetus, perhaps it came from something outside. These external models are called exogenic, from a Greek word meaning born outside. And the most compelling of these models involves something that sounds almost like science fiction. The idea is that Iapetus once had its own ring, just as Saturn is famous for its magnificent rings of ice and rock, Iapetus might have been circled by a smaller ring of debris in the distant past. This ring would have orbited around the Moon's equator, held in place by gravity. Over time, the material in the ring would have slowly spiraled inward and fallen onto the surface. As this debris rained down, it would have piled up along the equator. Layer after layer of icy rubble would have accumulated, building a ridge that followed the line of the ring exactly. The precision of the ridge would come from the precision of the orbit. Debris falling from a ring naturally lands along the equatorial plane. But where would this ring have come from? One possibility is that Iapetus was struck by a large object early in its history. A collision with a big enough impactor could have thrown a tremendous amount of debris into orbit around the Moon. Some of this debris would have escaped into space. Some would have fallen back immediately, but a portion might have stayed in orbit, forming a temporary ring. Over time, this ring would have been unstable. Tidal forces from Saturn would have tugged at the debris, causing its orbit to decay. Slowly, the material would have spiraled inward, getting closer and closer to the surface until it finally fell. This model has several appealing features. It explains the precision of the ridge. It explains why the ridge is located exactly on the equator. And it provides a mechanism for building such a massive structure relatively quickly. But there is an even more detailed version of this idea that scientists find especially compelling. In this scenario, the giant impact that struck Iapetus did not just create a ring of loose debris. It created something more substantial, a small moon, a sub-satellite that orbited around Iapetus, just as Iapetus orbits around Saturn. This tiny moon would have been made of the same material as Iapetus itself. Ice and rock blasted into space by the collision, gathering together under its own gravity to form a single body. At first, it would have orbited at a safe distance, but over time, tidal forces would have changed its orbit. Here is where things get interesting. Iapetus itself was also experiencing tidal forces from Saturn. These forces were slowing down the Moon's spin, just as we discussed earlier. And as Iapetus slowed down, something surprising would have happened to the sub-satellite. When a moon despins, the tidal bulges it creates on its parent body shift position. This can cause objects orbiting the Moon to either drift outward or drift inward, depending on the exact circumstances. In the case of Iapetus, the sub-satellite would have been pushed inward. Slowly, over millions of years, the tiny moon would have spiraled closer and closer to Iapetus. Eventually, it would have crossed a boundary called the Roche limit. This is the distance at which tidal forces become stronger than the gravity holding a body together. Any moon that crosses the Roche limit gets torn apart. The sub-satellite would have been ripped to pieces. Its material would have spread out into a ring around Iapetus. And then, over more millions of years, that ring would have collapsed onto the surface, building the Great Equatorial Ridge. This model is elegant because it ties together several features of Iapetus that once seemed unrelated. First, it explains the ridge itself. The debris from the destroyed sub-satellite would naturally fall along the equator, creating a precise linear feature. Second, it explains the timing. By storing the material in a sub-satellite, the model delays the formation of the ridge until after Iapetus had cooled and stiffened. This allows the ridge to form on a surface that was already rigid enough to support its weight without slumping. Third, it helps explain why Iapetus is the only moon with such a feature. Very few moons in the solar system have conditions that would allow this sequence of events to occur. The Moon needs to be far enough from its planet to have a large gravitational zone of influence. It needs to have experienced a giant impact that created a subsatellite. And it needs to have despin in a way that pushed that subsatellite inward. Iapetus checks all these boxes. Its great distance from Saturn gives it an unusually large zone of gravitational influence, called the Hill sphere. This means it could have held onto a subsatellite for a long time. And its location in the outer solar system made it a target for debris from the chaotic early days of planetary formation. Other moons are too close to their planets. Their Hill spheres are too small. Any subsatellite they might have had would have been quickly swept away. Only Iapetus, sitting alone in the cold darkness far from Saturn, had the right conditions for this remarkable sequence of events. There is one more piece of evidence that supports this model, and it has to do with the shape of Iapetus itself. Remember how we said that Iapetus is slightly flattened at the poles and wider at the equator than it should be? This unusual shape suggests that the Moon once spun much faster, and the sub-satellite model requires exactly this. The despinning of Iapetus is what would have pushed the sub-satellite inward to its destruction. So the shape of Iapetus and the existence of the ridge might be connected. Both could be signatures of the same ancient event, a giant impact that created a sub-satellite, followed by a long, slow dance of tidal forces that ended with the Moon tearing itself apart and falling onto the equator below. It is a dramatic story, a story of violence and transformation played out over hundreds of millions of years. And while we cannot know for certain that this is what happened, it remains one of the best explanations scientists have come up with. But there are still mysteries left to solve. One of the biggest unanswered questions is why the ridge is mostly confined to the dark hemisphere of Iapetus. If debris fell from a ring, we would expect it to land all the way around the equator, not just on one side. Yet the ridge is strongest and most continuous within Cassini ratio. On the bright side of the Moon, it breaks up into isolated peaks. Some scientists think this might be related to the timing of events. Perhaps the dark coating arrived before the ridge formed, changing the properties of the surface in ways that affected how the debris accumulated. Or perhaps the ridge formed first, and later processes erased parts of it on the bright side. Another possibility is that the ring itself was not perfectly uniform. If the debris was clumped or uneven, it might have fallen more heavily on one side than the other. The details depend on exactly how the subsatellite was destroyed and how its material spread out into a ring. These questions remain open, and they will probably stay open until we send another spacecraft to Iapetus for a closer look. The only close encounter we have had so far was that single flyby by the Cassini spacecraft in September of 2007. On that day, Cassini swooped past Iapetus at a distance of just over 1,200 kilometers. Its cameras captured stunning images of the surface in detail never seen before. But even with those images, there is so much we do not know. We do not know the exact composition of the ridge. Is it made of the same material as the rest of the surface? Or is it different, perhaps richer in rocky material from the destroyed subsatellite? We do not know how thick the ridge is. Does it have deep roots extending into the crust? Or does it sit on top of the surface like a layer of snow piled up by the wind? We do not know what lies beneath the ridge. Are there hidden structures under the surface that played a role in its formation? Or is the crust simply a uniform shell of ice? To answer these questions, we would need to send a spacecraft specifically designed to study Iapetus, an orbiter that could circle the Moon for months or years, mapping every feature in detail. or perhaps a lander that could touch down on the ridge itself, analyzing the ice and rock up close. Such a mission is not planned right now, but someday, perhaps, we will return to Iapetus, and when we do, we will finally unravel the secrets of this impossible wall. Until then, the ridge remains one of the great mysteries of our solar system, a reminder that even after decades of exploration, there are still surprises waiting for us in the darkness between worlds. Let us take a moment now to imagine what it would be like to stand at the base of this ridge. You are on Iapetus. The surface beneath your feet is ice, hard as stone in the bitter cold. The ground is rough and cratered, marked by billions of years of meteor impacts. Above you, the sky is black. There is no blue, no white clouds, no atmosphere at all. Just an endless void filled with stars. Saturn hangs in the sky, enormous and beautiful. You can see the planet's rings stretching out on either side, thin and bright against the darkness. The rings are edge-on from this angle, because Iapetus orbits far from the equatorial plane of Saturn. You can trace them from one side of the giant planet to the other, a line of light cutting across the sky. The sun is there too, but it is small, just a very bright star, too far away to warm your face. The light it casts is dim, like twilight on Earth. Everything is painted in shades of grey and pale gold, and in front of you, rising from the frozen ground, is the ridge. It does not look like any mountain you have ever seen. On Earth, mountains have foothills. They rise gradually, giving you a sense of their scale as you approach. But the ridge on Iapetus is different. It simply begins. One moment you are on flat terrain, and the next you are at the foot of a wall that stretches up and up into the sky. The slopes are steep. In some places they rise at angles of 30 degrees or more. The ice is rough and uneven, carved by ancient impacts and fractured by the stresses of billions of years. There are no smooth paths, no easy routes to the top, just ice and rock and shadow. If you could climb this wall, it would take days. Even in the weak gravity of Iapetus, the ascent would be exhausting. You would have to find handholds in the frozen surface, pull yourself up meter by meter, rest in whatever sheltered spots you could find. The cold would seep through your suit. The silence would press against your ears. As you climbed higher, the view would change. The horizon would drop away below you. The curvature of the moon would become visible. You would see the dark surface of Cassini Regio spreading out in all directions, pocked with craters like the face of an old battlefield. Near the top, the ridge narrows, the slope steepens, and then suddenly, you are standing on the crest, a knife edge of ice and rock with nothing above you but stars. From this height, you can see for hundreds of kilometers in every direction. To one side, the dark hemisphere stretches away, absorbing the faint sunlight. To the other side, you catch glimpses of the bright hemisphere, gleaming white against the black sky. The contrast is startling. Two halves of the same world, as different as night and day. The ridge continues in both directions, following the curve of the equator. It rises and falls, breaks and reforms, but always it follows that invisible line around the middle of the moon. You are standing on one small section of a structure that stretches for over 1,000 kilometers, and you have no idea how it got here. That is the mystery of Iapetus. That is the puzzle that scientists are still trying to solve. A wall that defies explanation. A feature that should not exist on a world this small and this cold. But perhaps that is what makes it so wonderful. The universe is full of things we do not understand. Every answer we find leads to new questions. Every mystery we solve reveals deeper mysteries beneath. Iapetus is a reminder that our solar system is still strange and wild and full of surprises. Even after centuries of watching the sky, even after sending robot explorers to every corner of our cosmic neighborhood, there are still places that can take our breath away. And as you stand on that ridge, looking out at the frozen surface and the distant rings of Saturn, you realize something else. You are not just seeing a moon. You are seeing history. Billions of years of history written in ice and rock. The story of a world that formed in the chaos of the young solar system, that was struck by ancient impacts, that watched its own small moon spiral inward and fall. The story of material raining down from above, building a wall that would last for ages. It is a story that is still being written. Somewhere out there, in the archives of space agencies and universities, scientists are studying the images from Cassini. They are building computer models and running simulations. They are arguing about theories and gathering evidence. And slowly, piece by piece, they are putting together the truth about this strange little world. Perhaps you will live to see the day when a new spacecraft arrives at Iapetus. Perhaps you will watch as images come back showing details we have never seen before. Perhaps the mystery of the ridge will finally be solved in your lifetime. Or perhaps the mystery will endure. Perhaps there will always be something about Iapetus that we do not quite understand. Some piece of the puzzle that does not fit. Some question that lingers in the back of our minds. Either way, the ridge will still be there, standing silent in the darkness, waiting for the next visitor from Earth. Now let us turn our attention to another aspect of this mysterious moon. We have talked about the ridge and the two-tone coloring, but Iapetus has other secrets to share. Secrets that help us understand the larger story of how it formed and evolved. One of these secrets has to do with the shape of Iapetus itself. Most moons and planets are roughly spherical. Gravity pulls everything toward the center, and over time, the material settles into a ball. But perfect spheres are rare in nature. Rotation causes bulging at the equator. Internal forces create bumps and depressions. The surface is always a little bit uneven. Iapetus is more uneven than most. When scientists measured the exact shape of Iapetus using data from the Cassini spacecraft, they found something surprising. The moon is flattened at the poles by about 34 kilometers. That is far more than expected for an object that rotates as slowly as Iapetus does today. Remember, Iapetus takes 79 days to complete one spin. At that leisurely pace, the outward force from rotation is tiny. The moon should be almost perfectly round, but instead, it is squashed, as if someone had pressed down on the top and bottom. This flattening tells us that Iapetus used to spin much faster. The shape we see today is a frozen relic of that earlier time. When the moon was young, it might have spun every 16 or 17 hours. At that speed, the equatorial bulge would have been significant. But then Saturn's gravity went to work. Tidal forces slowed the spin year by year, century by century. The rotation rate dropped, but the shape did not fully adjust. The outer shell of Iapetus had already hardened, locking in the bulge like a cast frozen around a broken bone. This is unusual. Most bodies in the solar system have had time to relax into shapes that match their current rotation. Iapetus is one of the few exceptions. Its shape is out of equilibrium, a snapshot of the past preserved in ice. And here is where things get interesting. The ridge sits right on top of this bulge. It adds even more height to an equator that was already wider than it should be. The combination gives Iapetus its distinctive walnut shape, with a raised seam running around the middle. Are the bulge and the ridge connected? Did they form through the same process? Or are they separate features that just happen to coincide? These are questions that scientists are still debating. One possibility is that the ridge formed specifically because of the bulge. Perhaps the equatorial region was a weak point, a place where material could pile up more easily. Or perhaps the bulge focused the stress from despinning, causing the crust to buckle right along the equator. Another possibility is that the ridge formed first, and its weight somehow affected the shape of the moon. A mountain range that massive would exert significant gravitational pull. It might have influenced how Iapetus adjusted to its slowing rotation. A third possibility is that the two features are unrelated. The bulge could be a remnant of fast spin, while the ridge came from a ring of debris falling from space. The coincidence of their location along the equator might just be a coincidence. We do not have enough information yet to know which of these possibilities is correct, but the connection between the ridge and the bulge is one of the most intriguing aspects of the Iapetus mystery. There is also the matter of what the ridge is made of. We know that Iapetus is composed mostly of water ice, with a small fraction of rocky material mixed in. The average density of the moon is only slightly higher than water, which tells us that ice dominates the composition. But the ridge might be different. If the ridge formed from debris falling from a ring, that debris would have come from the destroyed subsatellite. The subsatellite itself would have been made of material blasted off of Iapetus in a giant impact. But the composition of this material might not have been the same as the average composition of the moon. When an impact occurs, different materials respond in different ways. Rock tends to be ejected at higher velocities than ice. This means that the debris cloud from an impact might be enriched in rock compared to the original body. The subsatellite that formed from this debris might have been rockier than Iapetus itself. If so, the ridge could contain a higher proportion of rock than the surrounding surface. This might explain why it has held its shape so well over billions of years. Rock is more rigid than ice. A ridge made partly of rock would resist slumping and erosion better than a ridge made of pure ice. Unfortunately, we cannot test this hypothesis from the images alone. We would need some kind of spectroscopic measurement to determine the composition of the ridge compared to the rest of the surface. Or we would need to send a lander that could analyze the material directly. These measurements have not been made. They await a future mission that can return to Iapetus with the right instruments. For now, we can only speculate based on what we know. And what we know is remarkable enough. We know that Iapetus is a world divided, one side bright, one side dark, a moon that looks like it was dipped in ink. We know that it carries a ridge along its equator, a wall of mountains that rivals the tallest peaks in the solar system, a feature so precise that it seems almost designed. We know that the moon has an unusual shape, flattened at the poles, bulging at the equator. A frozen snapshot of a time when it spun much faster than it does today. We know that it orbits far from Saturn in a region of space where few other large moons are found. It travels on a path inclined to the plane of Saturn's rings, looking down on the great bands of ice and rock from a unique angle. And we know that all of these features might be connected, parts of a single story that began billions of years ago and left its mark on the surface we see today. The story of Iapetus is a story of transformation. A small icy world, born in the chaos of the early solar system, shaped by collisions and tides and the slow passage of time. a moon that carries the scars of its history on its face, written in ice and rock and shadow. It is a story that is still being told, and we are fortunate to be alive at a time when we can read parts of it. As we continue to drift through this long cosmic night, let us hold on to that sense of wonder. The universe is vast and old and full of mysteries, but we are explorers, we are curious. And every mystery is an invitation to learn. Let us now journey deeper into the details of this strange moon. Let us explore the textures and features of the ridge itself and see what they can tell us about how it formed. When scientists examined the high-resolution images from Cassini, they noticed something important about the ridge. It is not a single uniform structure. In different places, it takes on different forms. In some areas, the ridge appears as a single massive spine, a continuous wall of ice and rock that marches along the equator without interruption. The slopes are steep. The crest is sharp. It looks like the backbone of some enormous frozen creature, lying asleep beneath the surface. In other areas, the ridge splits into 2 or even 3 parallel ridges. These run side by side along the equator, like the lanes of a highway. The valleys between them are narrow and deep, carved by some process that we do not fully understand. In still other areas, the ridge breaks up entirely. It becomes a series of isolated peaks, standing alone like sentinels along the equatorial line. These peaks can reach heights of 10 kilometers or more. They rise abruptly from the surrounding plains, their slopes steep and their summits pointed. This variation tells us something important. Whatever process created the ridge was not perfectly uniform. There were differences from place to place, perhaps in the rate at which material accumulated, or in the properties of the surface onto which it fell. If the ridge formed from a ring of debris, this variation makes sense. Rings are not perfectly smooth. They have clumps and gaps. The density of material varies from one place to another. As the ring collapsed onto the surface, different amounts of debris would have fallen in different areas. The triple ridges are especially interesting. Some scientists think they might have formed when the ring had multiple layers or bands. As each layer fell, it created its own ridge, slightly offset from the others. The result would be a series of parallel structures, just like what we see. Another possibility is that the triple ridges formed through some kind of tectonic process. Perhaps the surface buckled in response to the weight of the falling debris, creating folds that appear as multiple parallel ridges. This would require the crust to be somewhat flexible at the time, able to deform under stress. The isolated peaks along the bright hemisphere are also intriguing. Remember, the ridge is strongest and most continuous within the dark Cassini regio. On the bright side, it fragments into separate mountains. One explanation for this is erosion. The bright hemisphere reflects more sunlight than the dark hemisphere. This might seem like a small difference, but over billions of years, even small differences can add up. The slightly warmer temperatures on the bright side could have caused more sublimation of ice from the ridge, wearing it down and breaking it apart. Another explanation involves the dark coating itself. Perhaps the dark material acted like a protective blanket, shielding the ridge from erosion. Without this coating, the bright side of the ridge was more exposed and degraded more quickly. A third explanation is that the ridge was never as well developed on the bright side to begin with. If the ring debris was unevenly distributed, more of it might have fallen on the dark hemisphere. The ridge would have been thinner and less continuous on the bright side from the start. We cannot yet determine which of these explanations is correct. But the pattern of variation along the ridge is an important clue that any successful theory will need to explain. Now let us talk about the slopes of the ridge. When you look at a mountain on Earth, you expect to see certain things. A gradual rise at the base, steeper slopes higher up, perhaps some cliffs or rock faces where the terrain is especially rugged. These features reflect the processes that built the mountain and the materials it is made of. The ridge on Iapetus has slopes that are surprisingly steep. In many places, they rise at angles of 30 degrees or more. This is close to what geologists call the angle of repose, the maximum slope at which loose material can pile up before it starts to slide down. When you pour sand onto a flat surface, it forms a cone with a certain slope. If you try to make the slope steeper, the sand slides down. The angle of repose depends on the size and shape of the grains and how well they lock together. For most loose materials, it is somewhere between 25 and 40 degrees. The fact that the ridge has slopes close to this angle suggests that it might have formed from material that simply piled up on the surface. Debris falling from a ring would accumulate in layers, building higher and higher until the slopes reach the maximum stable angle. Then the material would start to slide down, spreading outward at the base. This is consistent with the ring model. It is less consistent with models that involve material being pushed up from below. If the ridge formed through tectonic buckling or volcanic intrusion, we would expect different slope patterns. The material would be compressed and deformed, not just piled loosely on top. However, there is a complication. Some scientists who measured the slopes of the ridge found that they are actually a bit shallower than the angle of repose. This led them to argue that an external origin was not possible. How could material pile up to form a ridge if the slopes never reach the maximum stable angle? The answer might be that the angle of repose on Iapetus is different from what we would expect on Earth. In very low gravity, with very fine-grained icy material, the grains might lock together more tightly than usual. The slope could be maintained at a lower angle because the material is more cohesive. Or perhaps the ridge has settled over time. Even if it originally formed with steeper slopes, billions of years of small adjustments could have gradually reduced the angle. Ice creep, meteor impacts, and thermal cycling could all contribute to this slow relaxation. These are technical details, but they matter. Getting the slope measurements right is essential for testing the different theories of ridge formation, and the data we have so far is not quite good enough to settle the question definitively. We need more measurements, better images, perhaps even samples from the ridge itself. Until then, the slopes remain part of the puzzle. Let us now consider the question of timing. One of the most important things about the ridge is that it is old, very old. The craters that cover its surface tell us that it has been sitting there for billions of years, exposed to the steady rain of meteors that falls on everything in the solar system. By counting the craters and comparing them to crater counts on other surfaces, scientists can estimate relative ages. More craters mean an older surface. Fewer craters mean a younger surface. When this analysis was done for the ridge, the results were interesting. The ridge appears to be somewhat younger than the surrounding terrain. Not by much, both are ancient, but the ridge seems to have formed after the main surface of Iapetus was already in place. This is important because it rules out some theories. If the ridge were the same age as the rest of the Moon, we might think it formed during the initial assembly of Iapetus from the disk of material around Saturn. But the age difference suggests that the ridge formed in a separate event, sometime after the Moon had already taken shape. The ring model fits this timing well, a giant impact could have occurred millions or even hundreds of millions of years after Iapetus formed. The sub-satellite that was created would have orbited for a while before spiraling inward and breaking apart. And then the ring, debris, would have taken additional time to fall onto the surface. All of this adds up to a ridge that is slightly younger than the main surface. Exactly what we observe. The timing also matters for another reason. It tells us that the ridge formed when Iapetus was already cold and rigid. Remember, we said earlier that the ridge shows no signs of flexure. It sits on the surface like a weight on a stiff board, without bending the crust beneath it. This means the crust must have been strong enough to support the ridge from the moment it formed. For the crust to be this strong, the moon had to be very cold. The heat from Iapetus's formation had to have dissipated almost entirely. Scientists have calculated that the heat flow at the time the ridge formed could have been no more than a few milliwatts per square meter. That is almost nothing. For comparison, Earth's average heat flow is about 80 milliwatts per square meter. This extreme cold would not have been reached until at least 1 billion years after Iapetus formed, perhaps longer. The ridge is ancient, but not as ancient as the moon itself. There was a gap of time between when Iapetus came together and when the ridge appeared on its surface. The ring model explains this gap naturally. The sub-satellite stored the debris in orbit, keeping it from falling onto the surface immediately. Only when the orbit decayed did the material come down. By that time, the moon was frozen solid, ready to support whatever landed on it. Other models have more trouble explaining this timing. If the ridge formed through internal processes like despinning or convection, we would expect it to have happened early in Iapetus's history, when the interior was still warm and active. But the lack of flexure tells us the ridge formed late, when the moon was already cold. This is one of the strongest pieces of evidence in favor of the external origin hypothesis. The timing fits the ring model better than any internal model that has been proposed so far. Of course, science is always provisional. New data could change our understanding. Perhaps some internal process that we have not yet imagined could also produce a ridge that forms late in the moon's history. We should keep our minds open to possibilities. But for now, the ring model remains the leading explanation. Let us take a moment to appreciate what this model implies. If the ridge formed from a collapsing ring, then at some point in the distant past, Iapetus was circled by a band of debris. This ring would have been visible if anyone had been there to see it. A thin, bright line stretching across the sky, made of countless chunks of ice and rock. The ring would not have lasted forever. Slowly, over millions of years, it would have spiraled inward. The inner edge would have approached the surface, raining material onto the equator. The outer edge would have followed, adding more and more debris to the growing ridge. Eventually, the ring would have been gone. All the material would have fallen. The ridge would have been complete, standing silent and alone on the frozen surface. And then the ages would have passed. Meteors would have fallen, cratering the ridge and the surrounding plains. The dark coating from Phoebe would have arrived, painting one hemisphere black. The ice would have migrated, making the bright side brighter and the dark side darker. Through it all, the ridge would have remained, a monument to an event that happened billions of years ago, a record of a moon that no longer exists, preserved in the ice of the world it once orbited. It is a poetic image, a moon within a moon, a satellite of a satellite, a tiny world that lived and died in orbit around Iapetus, leaving behind only this great ridge as its grave marker. We cannot know for certain if this is what happened. the subsatellite is long gone, along with any direct evidence of its existence. But the ridge is real. It is there, waiting for us to understand it. And the more we study it, the more the ring model seems to fit. Let us now turn our attention to the broader context of Iapetus within Saturn's system. Saturn has dozens of moons. More than 100 have been discovered, ranging from tiny chunks of rock only a few kilometers across to Titan, a world larger than the planet Mercury. These moons orbit at different distances, have different compositions, and have experienced different histories. Among the large moons, Iapetus stands out for several reasons. First, there is its distance. Iapetus orbits at an average distance of over 3.5 million kilometers from Saturn. That is more than twice as far as Titan, the next closest major moon. Most of Saturn's other large moons cluster relatively close to the planet, within 1 million kilometers or so. Iapetus is the loner, wandering alone in the outer darkness. Second, there is its orbital inclination. Most of Saturn's moons orbit in the same plane as the planet's rings. They circle around the equator more or less. But Iapetus is tilted. Its orbit is inclined by about 15 degrees to Saturn's equatorial plane. This is unusual. Regular moons, the ones that formed in place around a planet, usually orbit close to the equatorial plane. The tilted orbit of Iapetus suggests that something knocked it out of alignment at some point, or that it formed in an unusual way. One idea is that Iapetus was disturbed by an encounter with another massive object. Perhaps a large moon passed close by, trading orbital energy and changing Iapetus's path. Or perhaps a massive body from outside the Saturn system passed through and stirred things up. Another idea is that Iapetus formed earlier than the other moons, when the disk of material around Saturn was still settling into the equatorial plane. It might have gotten stuck in its inclined orbit before the disk flattened out. A third idea involves Titan, the largest moon of Saturn. Titan is so massive that it dominates the gravitational environment of the Saturn system. Its presence affects the orbits of all the other moons. Some scientists think that interactions with Titan might have pumped up the inclination of Iapetus over time. Whatever the cause, the inclined orbit of Iapetus has an interesting consequence. From the surface of Iapetus, you would have a unique view of Saturn's rings. Most of Saturn's moons see the rings edge on, because they orbit in the same plane. But Iapetus looks down at the rings from an angle, getting a view that no other major moon can match. Third, there is the matter of Iapetus's origin. Where did this moon come from? Most large moons in the outer solar system are thought to have formed from disks of material around their parent planets. Just as the Sun was surrounded by a disk of gas and dust that gave rise to the planets, Jupiter and Saturn were each surrounded by smaller disks that gave rise to their moons. The regular moons, those that orbit in the equatorial plane and have circular orbits, clearly formed this way. They were born from the same disk as the planet itself. But Iapetus is not quite regular. Its inclined orbit sets it apart. And its composition, which is dominated by ice with only a small fraction of rock, is not quite the same as some of the other moons. One possibility is that Iapetus formed from a different part of Saturn's disk than the inner moons. Farther out, where the material was colder and more ice-rich, a moon like Iapetus could have coalesced. Another possibility is that Iapetus is older than the inner moons. Some recent studies have suggested that the moons inside Titan's orbit are surprisingly young, perhaps only a few 100 million years old. They might have formed from the debris of earlier moons that collided and broke apart. Iapetus, orbiting far from this violence, might be one of the original moons of Saturn, a survivor from the early days. This idea is speculative, but if true, it would make Iapetus even more special. A relic from the ancient past, carrying secrets about the early history of the Saturn system. The connection to other moons is also interesting. We mentioned earlier that the dark material on Iapetus probably comes from Phoebe, a small dark moon that orbits in the outer reaches of Saturn's gravitational influence. Phoebe is thought to be a captured object, a wanderer from the Kuiper belt that got caught by Saturn's gravity long ago. Phoebe orbits in the opposite direction from most of Saturn's moons, a telltale sign of capture. And it is dark, covered in the same kind of carbon-rich material that coats the leading hemisphere of Iapetus. When meteors hit Phoebe, they blast debris into space. This debris drifts inward, forming a vast, thin ring that is almost invisible. Iapetus, moving forward through its orbit, sweeps through this ring of dust, collecting the dark particles on its leading side. This connection links Iapetus to the larger story of Saturn's moon system. The same processes that brought Phoebe to Saturn have left their mark on Iapetus as well. The two moons, separated by millions of kilometers, are connected by a river of dust flowing through space. It is a reminder that the moons of Saturn do not exist in isolation. They are part of a system, connected by gravity and debris and the slow dance of orbits. What happens to one moon can affect another, even across the vast distances of the Saturnian realm. And speaking of connections, let us consider the possibility that Iapetus once had its own system of moons. This might sound strange. Moons having moons, it seems almost paradoxical. But there is nothing in the laws of physics that prevents it. Any object with enough gravity can hold smaller objects in orbit around it. The critical factor is something called the Hill sphere, the region of space where an object's gravity dominates over the gravity of its parent body. Inside the Hill sphere, a satellite can maintain a stable orbit. Outside it, the parent body will sweep away any debris. Iapetus has an unusually large Hill sphere for a moon of its size. This is because it orbits so far from Saturn. The farther a moon is from its planet, the larger its Hill sphere becomes. At over 3.5 million kilometers from Saturn, Iapetus has enough gravitational room to hold onto sub-satellites. We do not know of any current moons orbiting Iapetus. If any existed, the Cassini spacecraft would have spotted them. But in the distant past, things might have been different. The sub-satellite model for the ridge relies on this possibility. A giant impact created debris that coalesced into a small moon orbiting Iapetus. This moon existed for millions of years, slowly spiraling inward as tidal forces drained energy from its orbit. Eventually, it crossed the Roche limit and was torn apart, forming a ring that then collapsed onto the surface. This sequence of events requires Iapetus to have had a sub-satellite. It requires the right combination of orbital dynamics and timing, and it requires the Hill sphere to have been large enough to hold the sub-satellite for long enough. All of these conditions appear to have been met. Iapetus is one of the few moons in the solar system where such a scenario is plausible. Its unique position in the outer reaches of Saturn's domain gave it the space to host its own small moon, if only for a cosmic moment. It is a tantalizing thought. Somewhere in the depths of time, Iapetus might have had a companion, a small icy body that circled it, just as Iapetus circles Saturn. And the ridge is all that remains of that ancient partnership. Of course, this is still a hypothesis. a well-supported one, but a hypothesis nonetheless. We cannot prove that the sub-satellite existed. We cannot prove that it was destroyed and formed a ring. We can only say that this scenario explains the evidence better than any other idea that has been proposed. Science advances by building models and testing them against observations. The sub-satellite model is currently the best fit for what we know about Iapetus and its ridge. But new data could always change the picture. A future mission might discover something that supports the model or undermines it. That is how science works. We hold our theories lightly, ready to revise them when new evidence appears. We are not married to our ideas. We are married to the truth, whatever it turns out to be. And right now, the truth about Iapetus is still partially hidden, waiting for us to discover it. Let us continue our exploration of this mysterious moon. One aspect of Iapetus that we have not yet discussed in detail is its surface beyond the ridge. What does the rest of this world look like? What other features has it to show? The answer is that Iapetus is a world of craters. Impact craters cover virtually every part of the surface. Large craters, small craters, craters overlapping craters. Some are fresh, with sharp rims and bright ejecta blankets. Others are ancient and degraded, their edges worn down by billions of years of smaller impacts. The largest crater on Iapetus is called Turgis. It has a diameter of about 580 kilometers, which is nearly 40% of the moon's diameter. Imagine a crater on Earth that stretched from New York to Detroit. That is the scale we are talking about. The rim of Turgis is steep and dramatic. In places, it rises more than 15 kilometers above the crater floor. This is another reminder of how weak gravity allows for taller topography. On Earth, a crater rim this high would collapse under its own weight. On Iapetus, it can stand for eons. Turgis and other large craters tell us about the violence of the early solar system. When Iapetus was young, it was bombarded by a rain of debris left over from the formation of the planets. Comets and asteroids slammed into its surface, carving out basins and throwing ejecta across the landscape. The fact that so many craters have survived tells us that Iapetus has been geologically quiet for a very long time. There has been no volcanism to resurface the terrain, no tectonic activity to disrupt the craters. Just the slow accumulation of impacts over billions of years. This makes Iapetus an ancient world. Its surface is a record of the distant past, preserved in ice like a fossil in stone. The ridge itself is cratered too. This tells us that it has been sitting on the surface for a very long time, exposed to the same bombardment as the rest of the moon. If the ridge had formed recently, it would have fewer craters than the surrounding terrain. But it has plenty of craters, indicating great age. There are also some interesting features on Iapetus that are related to the craters. Scientists have observed evidence of landslides on the slopes of some craters and on the flanks of the ridge. These landslides have traveled surprisingly long distances, sliding down the gentle slopes much farther than we would expect. On Earth, landslides slow down quickly because of friction. But on Iapetus, with its weak gravity and icy surface, the dynamics are different. Some scientists think the landslides might have been lubricated by ice that briefly melted due to friction, or by some other mechanism that reduced friction dramatically. These long run-out landslides are another piece of the puzzle. They tell us about the mechanical properties of the icy surface and the processes that shape it over time. Now let us talk about the dark material in more detail. We have mentioned that the dark material on Cassini Regio probably comes from Phoebe. But what exactly is this material made of? Spectroscopic observations suggest that it contains a mixture of substances. There are dark, carbon-rich compounds similar to the stuff found in primitive asteroids and comets. There are minerals that have been altered by water, suggesting that Iapetus, or its source material, was once wet. And there may be organic molecules, complex chains of carbon and hydrogen that are the building blocks of life as we know it. The exact composition is still uncertain. We've only been able to study the dark material from a distance using telescopes and spacecraft cameras. To really understand what it is, we would need to collect samples and analyze them in a laboratory. One thing we do know is that the dark material is thin. It forms a coating on the surface, not a thick layer. If you could scrape away the dark stuff, you would find brighter ice beneath. How thin is it? Estimates vary, but some scientists think it might be only a few centimeters to a meter thick in most places. That is remarkably thin for something that covers an entire hemisphere. The thinness of the dark coating creates an interesting problem. If meteors have been hitting the surface for billions of years, why haven't they punched through the dark layer to reveal the bright ice beneath? We would expect to see fresh, bright craters scattered across Cassini Regio, but we do not. Almost all the craters in the dark region are dark. This suggests that the dark material is being continuously renewed. As fast as meteors expose the ice beneath, new dark material settles on top, covering it up. The source must be ongoing, a steady drizzle of dust from Phoebe and other outer moons that keeps the dark coating fresh. Alternatively, the impacts themselves might be spreading dark material around. When a meteor hits, it vaporizes some of the surface and throws debris in all directions. This debris could include dark material that was concentrated in the ejector, spreading it over the newly formed crater. Whatever the mechanism, the dark coating on Iapetus is a dynamic feature, not a static one. It is maintained by processes that are still operating today, keeping one hemisphere of the moon dark while the other stays bright. The boundary between the dark and bright regions is one of the most striking features on Iapetus. When you look at images of the moon, your eye is drawn to this line, this sudden transition from black to white. In some ways, the boundary is sharper than you might expect. There are areas where the transition happens over just a few kilometers. Bright ice on one side, dark coating on the other, with very little grey in between. But the boundary is also complex. In places, it is marked by wispy streaks of dark material extending into the bright terrain. These streaks often run north to south, perpendicular to the equator. They look like trails of dark paint dragged across a white canvas. Scientists think these streaks might be related to the way ice sublimes and dark material settles. As ice evaporates from one spot and refreezes in another, it can leave behind concentrations of dark material. The patterns we see might reflect the direction of ice migration across the surface. The transition zone is also where the ridge becomes fragmented. As the ridge crosses from the dark hemisphere to the bright hemisphere, it breaks up into isolated peaks. The connection between the ridge and the color boundary is another puzzle that scientists are trying to solve. Is the ridge weaker in the bright regions because there was less material to build it? Or did the ridge originally extend all the way around, but then eroded away on the bright side? The answer could tell us a lot about the history of both features. Let us now consider what the future might hold for our understanding of Iapetus. As of today, no missions to Iapetus are planned. The Cassini spacecraft, which gave us our best views of the moon, ended its mission in 2017. It plunged into Saturn's atmosphere, burning up in the clouds to avoid any chance of contaminating the potentially habitable moons like Enceladus. But the data from Cassini lives on. Scientists are still analyzing the images and measurements that the spacecraft sent back. New papers are published every year, refining our understanding of Iapetus and its ridge. And someday, we will go back. The outer solar system is a frontier that we have only begun to explore. Saturn and its moons are full of mysteries waiting to be solved. Titan has lakes of liquid methane and a thick atmosphere that hides its surface. Enceladus has geysers shooting water into space from an underground ocean. And Iapetus has its impossible wall. A future mission to the Saturn system could include a dedicated flyby of Iapetus, or even an orbiter that circles the moon for an extended period. Such a mission could map the ridge in detail, measuring its height and width and slope at every point. It could analyze the composition of the surface, determining what the ridge is made of. It could probe the interior, revealing whether there are buried structures that played a role in the ridge's formation. A lander could be even more ambitious. Imagine a spacecraft that touches down on the surface of the ridge itself. It would collect samples of the ice, analyzing them for the first time. It would measure the mechanical properties of the surface, telling us how strong and rigid it is. It would photograph the terrain from ground level, giving us a view that no orbital camera can match. Such a mission is technically feasible. The challenges are mainly ones of cost and priority. There are so many fascinating destinations in the solar system, and only so much money and time to go around. Iapetus must compete for attention with Mars and Europa and Titan and a dozen other worlds. But the mystery of the ridge is compelling. It is one of the great unsolved puzzles of planetary science. And eventually, the pull of that mystery will draw us back. When we do return, we will come armed with new instruments and new questions. We will build on the foundation laid by Cassini and push into new territory. And we will finally learn the truth about how a small, icy moon came to carry a wall around its middle. Until then, we can only wonder. We can study the images and build our models and debate our theories. We can let our imaginations roam across the frozen surface, climbing those impossible peaks and looking out at the stars. And in our wondering, we join a tradition that stretches back centuries. Giovanni Cassini looked through his telescope and saw a moon that appeared and disappeared. Generations of astronomers puzzled over its two-tone appearance. The Voyager spacecraft sent back the first glimpses of enormous mountains. The Cassini spacecraft revealed the ridge in all its glory. Each generation has added to our knowledge. Each generation has passed the torch to the next. And now it is our turn to carry it forward. What will we discover? What new questions will we ask? What surprises will Iapetus have in store? We do not know, and that is the beauty of exploration. The journey is never finished. There is always more to learn, more to see, more to understand. Iapetus waits for us, patient and silent in the outer darkness. The ridge stands tall along its equator, a monument to forces we are still trying to comprehend. And somewhere in the frozen landscape, there are answers waiting to be found. Let us rest now, as we drift through the cosmos together. Close your eyes and picture the scene one more time. The frozen surface stretching away to the horizon. The dark sky filled with stars. Saturn hanging overhead, its rings a thin, bright line. And the ridge rising before you, a wall of ice and rock that climbs toward the heavens. You are standing at the base of something impossible, something that should not exist, yet does. And in that impossibility, there is wonder, there is mystery, there is the promise of discovery yet to come. The universe is vast and strange and full of surprises. Every time we think we understand how things work, we find something that challenges our assumptions. Iapetus and its ridge are one such challenge. They remind us that our knowledge is incomplete, that there are still secrets to uncover, that the cosmos still has the power to amaze. Take a deep breath. Let the silence of space settle around you. Feel the weight of billions of years pressing down on this ancient surface. You are connected to something larger than yourself. The same atoms that make up your body were forged in the hearts of stars. The same laws of physics that shape your world also shape the moons of Saturn. You are part of this universe, bound to it by forces you cannot see but can feel. And in that connection, there is peace. The ridge will still be there tomorrow, and the day after, and 1 billion years from now. It is patient. It is enduring. It has waited this long for us to understand it. It can wait a little longer. Rest now. Let the mysteries of Iapetus fill your dreams. Let the darkness of space wrap around you like a blanket. And know that when you wake, the universe will still be there, waiting to be explored. This is the story of the impossible wall, the mystery that defied the laws of space. A small moon in the outer reaches of the solar system, carrying a burden that no one can quite explain. It is a story that is not yet finished. There are chapters still to be written, discoveries still to be made, and you are part of that story, whether you know it or not. Every time you look up at the stars and wonder, you are contributing to humanity's great project of understanding. So keep wondering, keep asking questions, keep exploring, even if only in your imagination. The universe rewards the curious. And Iapetus, with its ridge and its mysteries, is one of the greatest rewards of all. Good night, travelers. Sleep well. And may your dreams carry you to distant worlds, where impossible walls rise from frozen plains, and the secrets of creation wait to be discovered. The ridge of Iapetus stands silent in the darkness, but it speaks to those who have ears to hear. It tells a story of violence and transformation, of moons that were and moons that are no more. It tells a story of the forces that shape worlds, operating on scales of time and space that dwarf our human lives. Listen to that story. Let it wash over you. And in the listening, find rest. The cosmos is your home. These moons, these planets, these distant stars, they are part of your heritage. The same forces that built them built you. The same matter that composes them composes you. You are stardust, dreaming of stars. And in that dream, anything is possible, even an impossible wall. Let us close with one final thought. Science is often described as a way of knowing, a method for separating truth from falsehood. And it is that. But it is also something more. Science is a way of wondering, a way of looking at the world and asking, why is it like this? How did it come to be? What other ways could it have been? When we look at the ridge on Iapetus, we are not just collecting data. We are engaging in an act of imagination. We are trying to picture events that happened billions of years ago, in a place we have never been, under conditions we have never experienced. This requires creativity. It requires the willingness to consider possibilities that seem strange or unlikely. It requires the humility to admit when we do not know the answer, and the persistence to keep searching anyway. The scientists who study Iapetus are doing this work. They are imagining subsatellites that no longer exist. They are modeling ring collapses that happened before the first life appeared on Earth. They are testing ideas against data and revising them when they do not fit. This is beautiful work. It is challenging and frustrating and deeply rewarding. And it is open to anyone who is willing to engage with it. You do not need to be a professional scientist to wonder about Iapetus. You do not need a degree or a laboratory or a spacecraft. All you need is curiosity. All you need is the willingness to ask, what is that thing, and how did it get there? That is how science begins, with a question, and questions can come from anyone. So as you drift off to sleep, carry a question with you. Let it float in your mind, unanswered but not forgotten. How did a moon this small end up with a wall this big? We do not know for certain. Not yet. But we are getting closer. Every observation, every model, every debate brings us a little nearer to the truth. And someday, we will know. Someday, the mystery of the ridge will be solved. The impossible will become the understood. And Iapetus will take its place in the catalogue of worlds we have come to comprehend. Until that day, the ridge remains a beacon, a signal from the outer darkness, calling to those who wonder. Come and see, it says. Come and understand. There are marvels here that you have not imagined. Secrets that will change how you see the universe. And we will answer that call. We always have. From the first human who looked up at the stars and wondered what they were, to the latest spacecraft beaming data back across billions of kilometers, we have been reaching outward. Trying to understand, trying to know. Iapetus is part of that journey. The ridge is a way station on the road to understanding. We have passed this way before, and we will pass this way again. So rest now. Let the journey continue in your dreams, and know that when you wake, the universe will be there, ready to be explored. The impossible wall of Iapetus, a mystery that defied the laws of space, a challenge to our understanding, an invitation to wonder. May you always accept that invitation. Good night, sweet dreams, and may the stars light your way. As we continue to drift through the outer reaches of the Saturn system, let us spend more time dwelling in the details of this remarkable world. There is so much more to explore, so many quiet corners of this mystery that deserve our attention. Consider for a moment the texture of the ridge itself. When you look at the high-resolution images captured by Cassini, you can see individual boulders and blocks of ice scattered along the slopes. Some of these are enormous, as big as houses or small apartment buildings. They sit on the surface, tumbled down from higher elevations, coming to rest wherever gravity and friction allowed. These boulders tell us about the processes that shape the ridge over time. Meteor impacts shake the ground, loosening material that then slides downward. The thermal cycle of day and night, even though the temperature changes are small by our standards, causes the ice to expand and contract ever so slightly. Over billions of years, these tiny expansions and contractions can work boulders loose from the surface. The distribution of boulders might also tell us about the original structure of the ridge. If the ridge formed from falling debris, we would expect a certain distribution of block sizes. If it formed through tectonic processes, the distribution might be different. Unfortunately, the resolution of our images is not good enough to study these boulders in detail. We can see that they are there, but we cannot measure them precisely or map their distribution comprehensively. This is another task for a future mission. Imagine a rover crawling across the slopes of the ridge, photographing every boulder and analyzing the ice beneath it. Such a mission could tell us more about the ridge's formation than any number of orbital observations. But rovers on icy moons are still beyond our current capabilities. The challenges of operating in such extreme cold so far from Earth are immense. Someday we will solve them, but not yet. For now, we must content ourselves with what we have, and what we have is remarkable enough. Let us talk more about the light and shadow on Iapetus. Because the ridge rises so high above the surrounding plains, it casts long shadows when the sun is low on the horizon. These shadows can stretch for dozens of kilometers, dark bands that cut across the surface like strokes of ink. In the images from Cassini, these shadows help reveal the shape of the ridge. They show where the slopes are steep and where they are gentle. They highlight the peaks and the valleys, the gaps and the continuous stretches. The interplay of light and shadow on Iapetus is particularly dramatic because of the moon's slow rotation. A single day on Iapetus lasts nearly 80 Earth days. This means that the sun rises and sets very slowly. The shadows creep across the surface, shifting position over the course of weeks. If you were standing on Iapetus, watching the sun rise over the ridge, the experience would be unlike anything on Earth. The sun would appear as a small, bright star on the horizon, barely distinguishable from the brightest stars around it. Over the course of several Earth days, it would climb higher, illuminating more and more of the ridge. The shadows would shrink, pulling back like a tide receding from the shore. Details that were hidden in darkness would be revealed. The full height and complexity of the ridge would become visible, and then, as the sun reached its highest point and began to descend, the process would reverse. The shadows would grow again, advancing across the surface, swallowing features in their path. This slow dance of light and shadow has been going on for billions of years, and it will continue for billions more. The ridge will stand, patient and silent, as the sun circles overhead again and again and again. There is something meditative about this thought. The incredible slowness of time on Iapetus, the vast patience of the cosmos. Things change, but they change so slowly that a human lifetime is barely a flicker. We live our lives in a hurry. We rush from one task to the next, always busy, always moving, but the universe moves at its own pace. The ridge on Iapetus does not care about our schedules or our deadlines. It simply exists, waiting for nothing, in no hurry at all. Let us take a lesson from that. Let us slow down, just for this moment, and appreciate the vastness of cosmic time. 1 billion years ago, the ridge was there. 1 billion years from now, the ridge will still be there. Our entire human history, everything our species has ever done, fits into a tiny sliver of that span. We are newcomers to the universe, brief visitors who have only just begun to explore. And yet we have learned so much. In just a few centuries of scientific inquiry, we have mapped the solar system, discovered the laws of physics, sent robots to distant worlds. We have seen the ridge on Iapetus with our own instruments, even though we cannot yet walk on its slopes. This is the power of the human mind, the ability to reach across time and space, to understand things we have never directly experienced. We are small, but our curiosity is vast, and that curiosity will carry us forward, to Iapetus and beyond. Now let us consider another aspect of this moon, the view from Iapetus itself. We have talked about what Iapetus looks like from the outside, but what would you see if you were standing on its surface, looking up at the sky? First, you would see Saturn. The great ringed planet would hang in the sky, always in the same position, because Iapetus is tidally locked. Saturn would appear about 40 times larger than the full moon appears from Earth. It would be a magnificent sight, a striped ball of gold and tan, wrapped in its famous rings. From Iapetus, the rings would not appear edge-on like they do from most of Saturn's moons. Because Iapetus orbits in an inclined plane, you would see the rings at an angle. They would form a bright, thin arc stretching across Saturn's face, tilted like the brim of a hat. The amount of tilt would change over time, as Iapetus precesses and as Saturn's seasons change. Sometimes the rings would be more open, showing their full width. Other times they would be nearly edge-on, almost disappearing from view. This changing view of the rings would be one of the unique experiences of living on Iapetus. No other major moon in the Saturn system gets to see the rings from this perspective. Beyond Saturn, you would see the stars. Thousands of them, bright and steady in the airless sky. Without an atmosphere to scatter the light, the stars would be visible even close to Saturn's glare. The Milky Way would stretch across the sky, a river of light made of billions of distant suns. And somewhere among those stars, too faint to see with the naked eye, would be Earth, our home, our birthplace, the world that sent the spacecraft that photographed this place, a tiny blue dot, invisible from so far away. The thought of looking back at Earth from Iapetus is both humbling and inspiring. Humbling because it reminds us how small we are. Inspiring because it shows how far we have reached. We have seen Iapetus. We have photographed it and mapped it and puzzled over its mysteries. Someday, perhaps, we will stand on its surface in person. And when that day comes, we will look back at Earth and know that we have traveled farther than our ancestors ever dreamed. Let us now return to the ridge and explore some of the finer details of its structure. One feature that scientists have noticed is that the ridge is not perfectly straight. If you trace its path along the equator, you find small deviations, slight curves and wiggles that depart from a perfectly straight line. These deviations are small, on the order of a few kilometers, but they are there, and they might tell us something about how the ridge formed. If the ridge formed from a ring of debris falling onto the surface, we would expect it to follow the equator very precisely. Debris in orbit around a body naturally falls along the equatorial plane. There should not be much deviation. But the equator of Iapetus might have shifted over time. If the ridge formed first, and then some event caused the moon to tip slightly on its axis, the ridge would no longer line up perfectly with the current equator. Such a shift could happen if a large impact hit Iapetus at an angle, transferring momentum and changing the orientation of the moon. Or it could happen through a process called true polar wander, where the distribution of mass on the surface causes the spin axis to shift. If the ridge caused such a shift, the heavy mass concentrated along the equator could have pulled the moon into a new orientation, aligning the ridge with the current spin axis. This is called reorientation, and it has been proposed for other bodies in the solar system. The small deviations we see in the ridge might be evidence of this process. They might mark the original path of the ridge before reorientation occurred, preserved as slight curves in an otherwise straight feature. This is speculative, of course. The deviations could have other explanations. Perhaps the ring that formed the ridge was not perfectly equatorial. Perhaps the surface beneath the ridge was uneven, causing the debris to pile up in slightly different places. But the possibility of reorientation is intriguing. It would mean that the ridge is even more important than we thought. Not just a mountain range, but a feature so massive that it altered the very orientation of the world it sits on. Another detail worth noting is the width of the ridge. We have mentioned that the ridge is typically 20 to 70 kilometers wide at its base, but this width varies along the length of the ridge. In some places, it is broader. In other places, it is narrower. These variations might reflect differences in the amount of material that fell in different locations. If the ring that formed the ridge had denser clumps in some regions, more material would have accumulated there, creating a wider ridge. Alternatively, the variations might reflect differences in the underlying surface. If the crust was weaker in some places, the debris might have spread out more, creating a broader base. If the crust was stronger, the debris might have piled up higher and narrower. Understanding these variations would require detailed mapping of the ridge from end to end. We would need to measure the width and height at thousands of points, correlating them with other surface features. This is the kind of work that a dedicated orbital mission could accomplish. Let us also consider the valleys and gaps in the ridge. The ridge is not continuous. There are places where it breaks, where the mountains give way to flat terrain before rising again further along the equator. These gaps are puzzling. If the ridge formed from a ring, why would there be breaks in it? One possibility is that the ring itself had gaps. Rings around planets and moons are not uniform. They have clumps and voids, places where material is concentrated and places where it is absent. The Cassini division in Saturn's rings is a famous example. A dark band where gravity from a moon has swept away material. If the ring around Iapetus had similar gaps, those gaps would show up in the ridge. The material would fall everywhere except in those regions, leaving breaks in the mountain chain. Another possibility is that the gaps formed later. Perhaps sections of the ridge collapsed or were eroded away. Meteor impacts could excavate material, creating breaks in the ridge over time. A third possibility involves the process of ring collapse itself. As the debris spiraled inward, it might have come down in waves or bursts. The timing of these waves might have left gaps between successive deposits. The gaps are not distributed randomly. Some sections of the ridge are well preserved, while others are more fragmented. Understanding the pattern of gaps could help us determine which of these explanations is correct. Let us spend a moment now considering the color of the ridge. In most images, the ridge appears dark because it lies within Cassini Regio, the dark hemisphere of Iapetus. The same dark coating that covers the leading hemisphere also covers the ridge, but there are hints of color variation along the ridge. Some areas appear slightly lighter than others. Some areas have a reddish tinge. These color variations might reflect differences in the composition of the ridge material. Perhaps some sections have more rock and less ice. Perhaps some sections have been exposed more recently by meteor impacts, revealing fresher material beneath. The reddish color is particularly interesting. Red colors in the outer solar system are often associated with organic molecules, complex carbon compounds that have been altered by radiation. The presence of such material on the ridge could tell us about the composition of the ring that formed it. We would need more detailed spectroscopic observations to fully understand these color variations. The Cassini spacecraft did carry instruments capable of such measurements, but the limited number of flybys meant that only a small portion of the ridge was studied in detail. A future mission, with more time to spend at Iapetus, could map the entire ridge spectrally, correlating color and composition with physical features. This would give us a much more complete picture of what the ridge is made of and how it formed. Now let us turn our attention to the question of stability. We have said that the ridge has survived for billions of years. But how stable is it really? Is it slowly changing, gradually wearing down? Or is it frozen in place, unchanging over timescales we can scarcely imagine? The answer is probably somewhere in between. On one hand, the ridge shows remarkable preservation. Its slopes are still steep. Its peaks are still sharp. The overall shape has not collapsed or slumped in any obvious way. On the other hand, the ridge is not completely static. Meteor impacts continue to chip away at it, one small crater at a time. The thermal cycling, though extreme cold limits its effects, still works on the ice over very long periods. And there may be other processes at work that we have not yet identified. The boulders we see on the slopes of the ridge are evidence of ongoing change. They roll down from higher elevations at some point. They will continue to move slowly as the ridge adjusts to the forces acting on it. But these changes are extremely slow. A boulder might shift once every million years. A peak might lose a few meters of height over 100 million years. On human timescales, the ridge appears frozen and eternal. This is the nature of geology on small, cold bodies. Without the heat and activity that drive change on worlds like Earth, surfaces can remain unchanged for eons. Iapetus is a time capsule, preserving features from the ancient past in a way that larger, warmer worlds cannot. The ridge is part of this preservation. It has survived longer than anything humans have ever built. It will continue to stand long after our species is gone, and it will remain there, marking the equator of this small moon, until some event finally erases it. What could erase the ridge? A sufficiently large impact could do it. If a comet or asteroid big enough struck Iapetus, it could destroy the ridge along with much of the moon's surface. Such impacts are rare in the modern solar system, but they do happen on timescales of billions of years. The gradual warming of the sun could also play a role. In about 5 billion years, the sun will enter its red giant phase, swelling enormously and increasing its energy output. The outer solar system will warm, and the ice on bodies like Iapetus will begin to sublimate. If enough ice is lost, the ridge might lose its structural integrity. It might slump and spread, losing its sharp profile. Or it might simply evaporate, molecule by molecule, until nothing is left but a thin layer of rocky debris. But these are concerns for the very distant future. On any timescale relevant to humans, the ridge is effectively permanent. Let us now spend some time with the poetic side of this mystery. There is something profound about a wall that circles a world. Walls have meaning in human culture. They divide and protect. They mark boundaries. They are symbols of power and permanence. The ridge on Iapetus is not a wall in the human sense. It was not built by anyone. It serves no purpose that we can discern. And yet, it carries the weight of symbolism nonetheless. Looking at the ridge, you cannot help but feel that you are seeing something significant, something that matters. The precision of its placement, the grandeur of its scale, the mystery of its origin, all these things combine to create a sense of awe. The ancients who named the stars and the planets would have loved Iapetus. They would have told stories about the Great Wall, weaving it into their myths of gods and heroes. They would have seen meaning in its placement along the equator, dividing the moon into two halves. We moderns are more cautious about seeing meaning where there is none. We know that the ridge is a product of natural forces, not divine will. And yet the sense of awe remains. This is one of the gifts of science. It does not diminish wonder. It enhances it. Knowing that the ridge formed through the collapse of an ancient ring does not make it less marvelous. It makes it more marvelous because it connects the ridge to the vast, intricate processes that have shaped our solar system. The ridge is a thread in a tapestry that spans billions of years and billions of kilometers. Pull on that thread, and you find yourself connected to everything else. The formation of Saturn from the solar nebula, the assembly of the moon system, the long dance of gravity that slowed Iapetus and tore its sub-satellite apart, the rain of debris from Phoebe that darkened one hemisphere. All of these stories are woven together, and the ridge is where some of them become visible. Science is the art of finding these connections, of tracing the threads and seeing the pattern. And when the pattern is revealed, it is more beautiful than any story we could have invented. The ridge on Iapetus is real. It exists independently of our thoughts about it, but our thoughts about it have their own reality. Our wonder, our curiosity, our determination to understand, these are as much a part of the universe as the ice and rock of the ridge itself. In contemplating the ridge, we become part of its story. We add a new chapter, written in observations and theories and the careful work of science. And that chapter matters. It matters because understanding is valuable in itself, because knowledge is a form of treasure that grows richer the more it is shared. So let us continue to explore. Let us send our robots and our dreams to distant moons. Let us ask questions and seek answers. And let us never lose the sense of wonder that draws us to these mysteries in the first place. The ridge waits for us, patient, ancient, full of secrets, and we are coming. As we near the end of our journey tonight, let us summarize what we have learned about this impossible wall. Iapetus is a moon of Saturn, the third largest of its kind, orbiting far from the planet, in the cold outer reaches of the Saturnian system. It is a world of contrasts, with one hemisphere dark as coal and the other bright as snow, and running along its equator, like a seam on a toy ball, is a ridge that towers higher than any mountain on Earth. The ridge stretches for over 1,000 kilometers. It reaches heights of nearly 20 kilometers in places. It follows the equator with uncanny precision, deviating only slightly from a perfect geometric line. Scientists have proposed many theories to explain this ridge. Some involve forces from inside the moon, like the stress from despinning or the buckling of the crust as the interior cooled. Others involve forces from outside, like debris falling from a ring that once circled the moon. The most compelling theory today is that Iapetus once had a sub-satellite, a small moon of its own created by a giant impact early in its history. This sub-satellite spiraled inward over millions of years, pulled by tidal forces, until it crossed the Roche limit and was torn apart. The debris formed a ring around Iapetus, which then slowly collapsed onto the surface, building the ridge we see today. This theory explains many features of the ridge: its precise alignment with the equator, its great height, its ancient age, and the fact that no other moon in the solar system has anything quite like it. But the theory is not proven. There are still questions that remain unanswered. Why is the ridge mostly confined to the dark hemisphere? What is the exact composition of the ridge material? How do the ridge and the moon's unusual shape relate to each other? These questions await a future mission, a spacecraft that can return to Iapetus with new instruments and new observations. Until then, the ridge remains one of the great mysteries of our solar system. And what a wonderful mystery it is. In a universe full of wonders, the ridge on Iapetus stands out. It is a reminder that even after decades of exploration, there are still surprises waiting for us, still features that defy easy explanation, still puzzles that challenge our understanding. That is what makes science so exciting. The unknown is not something to fear, it is something to explore. Every mystery is an invitation to learn, to grow, to push the boundaries of what we know. The ridge on Iapetus is one such invitation, and someday we will accept it fully. We will send a spacecraft to orbit this strange moon. We will map every peak and valley. We will analyze every sample, and we will finally understand how this impossible war came to be. Until that day, the ridge waits, silent, patient, full of secrets, and we dream of the day when we will unlock them. Thank you for joining me on this journey tonight. Thank you for letting your curiosity carry you across the solar system to a small icy moon where wonders await. May you sleep well. May your dreams be filled with stars and moons and mysteries yet to be solved. And may you always keep that spark of wonder alive, the spark that draws us to the unknown, the spark that makes us human. Good night, travelers. The cosmos awaits, and the ridge on Iapetus will be there when you wake, standing tall, keeping its secrets, for now. Before we close our eyes and let sleep take us to distant places, let us dwell a little longer in the quiet beauty of the Saturn system. There is still more to see, more to feel, more to understand about this corner of the cosmos that holds such wonders. Think about what it means for Iapetus to exist at all. 4.5 billion years ago, there was no Saturn as we know it today. There was only a vast cloud of gas and dust, collapsing under its own gravity, beginning the long process that would create a planet and its moons. In that swirling disk of material, grains of ice and rock began to stick together. Small bodies grew larger. Larger bodies swept up, smaller ones, and gradually, over millions of years, the moons of Saturn took shape. Iapetus was born in this chaos. It assembled itself from countless fragments, each one carrying its own history. Some fragments came from the cold outer regions of the disk, where water ice was abundant. Others came from warmer regions, closer to the young planet, where rock dominated. The composition of Iapetus reflects this mixed heritage. It is mostly ice, but with a significant fraction of rock mixed in. The materials that make up this moon came from different places, different times, different conditions. And they came together to form a single world. This process of assembly was not gentle. The fragments that built Iapetus collided at speeds of kilometers per second. Each collision released tremendous energy, heating the material and sometimes melting it. The young moon was a violent place, constantly being battered by new arrivals. Eventually, the rain of debris slowed. The disk around Saturn dispersed, drawn into the planet or ejected into space, and Iapetus settled into its orbit, cooling and solidifying over millions of years. But the violence was not entirely over. At some point, perhaps hundreds of millions of years after the moon formed, a large object struck Iapetus. This impact was catastrophic. It blasted a vast amount of material into space, temporarily turning the moon into the center of its own debris cloud. Some of this debris fell back immediately, crashing onto the surface and adding more craters to an already battered landscape. Some escaped the moon's gravity entirely, drifting away into the vastness of space. But some stayed in orbit. It gathered together, coalescing under its own gravity, and formed a small companion moon. This was the sub-satellite, a child of violence, born from the collision of worlds. For a time, the sub-satellite orbited peacefully. It circled Iapetus just as Iapetus circled Saturn, a tiny echo of the larger system. Perhaps it was a few dozen kilometers across, perhaps larger. We do not know its exact size because it no longer exists. The fate of the sub-satellite was sealed by the same forces that governed the larger system. Saturn's gravity reached out and tugged at Iapetus, slowing its spin over millions of years. And as Iapetus slowed, the orbit of the sub-satellite began to decay. Tidal forces work in complex ways. When a moon spins faster than its satellite orbits, it tends to push the satellite outward. But when a moon spins slower than its satellite orbits, it tends to pull the satellite inward. As Iapetus despun, it crossed this threshold, and the sub-satellite began its long spiral toward destruction. Closer and closer it came. Year by year, century by century, millennium by millennium. The sub-satellite orbited lower and lower, its path tightening like a spring being compressed. And then it crossed the Roche limit. The Roche limit is the distance at which tidal forces overcome the gravity holding a body together. Inside this boundary, a moon cannot survive. The gravitational pull from the parent body is simply too strong. It stretches and tears, ripping the object apart. When the sub-satellite crossed this invisible line, its end was swift. The tidal forces from Iapetus stretched it beyond its ability to hold together. Cracks formed, chunks broke away, and within a geologically short time, the sub-satellite ceased to exist as a single body. In its place was a ring. The debris spread out into a disk around Iapetus, orbiting in the equatorial plane. Countless chunks of ice and rock, ranging from dust grains to boulders, circled the moon in a thin, bright band. This ring was not stable. It could not last forever. The same forces that had destroyed the sub-satellite continued to work on the debris. Particles at the inner edge of the ring spiraled downward, drawn by gravity. Particles at the outer edge drifted outward, eventually escaping. Over millions of years, the ring collapsed. The debris fell onto the surface of Iapetus, piling up along the equator where the ring had been. Layer upon layer accumulated, building higher and higher. And when the last of the debris had fallen, the ridge was complete. This is the story that scientists believe explains the impossible wall. A story of impact and creation, of tidal forces and orbital decay, of rings rising and falling. A story that spans hundreds of millions of years and involves processes that we can barely imagine. And all of it left its mark on this small, cold moon. The ridge is a monument to this history. It is the gravestone of the sub-satellite, the remnant of the ring, the record of forces that operated on scales of time and space far beyond our everyday experience. When you look at the ridge, you are looking at deep time made visible. Let us consider now the broader implications of this story. If Iapetus once had a sub-satellite and a ring, could other moons have had similar features? Could the moons of Jupiter or the moons of Uranus have experienced the same processes? The answer is that Iapetus may be special. Its unique position in the Saturn system gives it advantages that other moons do not have. First, there is its distance from Saturn. Iapetus orbits far from the giant planet, which means Saturn's gravitational influence is relatively weak. This gives Iapetus a large hill sphere, the region of space where its own gravity dominates. A larger hill sphere means more room for a sub-satellite to orbit stably. Second, there is the timing. The sequence of events that created the ridge required very specific conditions. The giant impact had to happen after Iapetus had formed, but while enough debris was still flying around to create a large ejecta cloud. The sub-satellite had to survive long enough for Iapetus to despin, which required the moon to be far enough from Saturn that tidal forces were relatively weak. And the ridge had to form after the moon's crust had solidified, so that it could support the weight without flexing. All of these conditions came together on Iapetus. They may not have come together anywhere else. This makes the ridge not just a mystery, but a precious artifact. It is evidence of a process that we can study in detail on only one world. By understanding how the ridge formed on Iapetus, we can learn about processes that might have occurred elsewhere, even if the evidence has been erased. The ridge is like a fossil. It preserves information about the past that would otherwise be lost. And like a fossil, it rewards careful study with insights that go far beyond the object itself. Let us also think about what the ridge can tell us about the materials that make up Iapetus. If the ridge formed from debris ejected by a giant impact, that debris would have come from deep inside the moon. The impact would have excavated material from beneath the surface, throwing it into space where it could collect into the sub-satellite and eventually fall back as the ridge. This means the ridge might contain samples of Iapetus's interior that are not found anywhere else on the surface. By studying the ridge, we might be able to learn about the composition of material that lies hidden beneath the ice. On Earth, we learn about the planet's interior by studying volcanic rocks and by measuring seismic waves. On Iapetus, we have neither volcanoes nor seismometers, but we might have the ridge, a natural excavation that brought deep material to the surface. A future mission could test this idea by comparing the composition of the ridge to the composition of the surrounding plains. If they are different, it would support the idea that the ridge contains material from depth. If they are the same, it would suggest that the ridge formed from surface material alone. Either answer would be valuable. Either answer would teach us something new. Let us now take a moment to appreciate the sheer beauty of Iapetus. Not just the ridge, but the whole moon, the sweeping curves of the dark and light hemispheres, the ancient craters, some fresh and bright, others worn and subtle. The texture of the ice, rough and chaotic in some places, smooth and flat in others. Iapetus is a world of visual contrasts. The yin-yang pattern of its surface makes it instantly recognizable. You could see this moon from millions of kilometers away and know immediately what it was. This distinctiveness has made Iapetus a favorite subject for artists and writers. Science fiction stories have been set on its surface. Paintings have depicted its strange landscapes. The moon has captured human imagination in a way that few other worlds have. Part of this appeal is the mystery. We are drawn to things we do not understand. The ridge, with its impossible precision and unknown origin, beckons us to explore. It promises secrets waiting to be uncovered. But part of the appeal is simply aesthetic. Iapetus is beautiful. Its patterns please the eye. Its proportions feel right somehow, in a way that is hard to articulate. Perhaps this is because the same physical laws that govern our world also govern Iapetus. The same gravity, the same chemistry, the same principles of thermodynamics. We are made of the same stuff, shaped by the same forces. Deep down, at the level of atoms and equations, we are kin. Looking at Iapetus, we see ourselves reflected. A small body in a vast cosmos, shaped by forces beyond our control, carrying the marks of our history on our face. We too have ridges and valleys, peaks and plains. We too are sculpted by time. This is the poetry of science, the recognition of kinship across the gulf of space, the understanding that we are not separate from the universe but part of it. Let us carry that understanding with us into sleep. As the hours of night pass and the stars wheel overhead, think about Iapetus. Think about the ridge standing silent in the darkness, bathed in the faint light of the distant sun. Think about the processes that built it, the impact that shattered a world, the sub-satellite that formed from the debris. the long, slow spiral toward destruction, the ring that rose and fell, the debris that piled up layer by layer over millions of years. Think about the time it took. Hundreds of millions of years. More time than humans have existed. More time than any civilization has stood. A span so vast that our minds can barely grasp it. And think about the fact that we know this, that we, small creatures on a small planet, have figured out the history of a distant moon. That we have sent machines across the solar system to photograph it, measured it, analyzed it. That we have taken the data and built theories and tested them against evidence. This is remarkable. This is one of the great achievements of our species. Not just to survive, but to understand. Not just to exist, but to know. The ridge on Iapetus does not care whether we understand it or not. It will be there regardless of what we think or believe. But our understanding matters to us. It enriches our lives. It expands our horizons. It connects us to something larger than ourselves. And that is worth celebrating. So tonight, as you drift toward sleep, let yourself feel connected to the cosmos. Feel the vastness of space, the depth of time, the wonder of existence. You are part of this universe. Your atoms were forged in stars that died before the Earth was born. Your body is made of the same elements that make up moons and planets. You are stardust, thinking about stars. And in that thought, there is peace. The mysteries of the universe are not threats to be feared. They are invitations to be accepted. Every unknown is an opportunity. Every question is a door waiting to be opened. The ridge on Iapetus is one such door. We have pushed it open a crack and glimpsed what lies beyond. But there is so much more to see, so much more to learn. Someday, we will open that door all the way. We will send spacecraft and rovers and perhaps even people to walk on the frozen surface of Iapetus. We will stand at the base of the ridge and look up at peaks that dwarf the mountains of Earth. And we will finally know the full truth of how this impossible wall came to be. Until that day, we dream, we imagine, we wonder, and in our wondering, we honor the spirit of exploration that has carried humanity from the savannas of Africa to the shores of distant moons. We are explorers. It is in our nature. And the ridge on the Iapetus calls to us, inviting us to continue the journey. Rest now. Let sleep come gently, like a tide washing over the shore. Tomorrow, the sun will rise, and the world will call you back to your daily tasks. But tonight, you can drift among the stars. Tonight, you can visit Iapetus in your dreams. The ridge will be there waiting for you. Tall and silent and full of mystery, a wall around a world, a monument to forces we are only beginning to understand. Good night, dear traveller. May your sleep be deep and peaceful. May your dreams carry you to places of wonder. And may you wake with a renewed sense of curiosity, ready to explore the mysteries that surround us every day. The universe is vast and strange and beautiful beyond measure, and you are part of it. Never forget that. Sleep well. The stars are watching over you. And the ridge on Iapetus stands silent in the darkness, keeping its secrets, waiting for the day when we will return to learn them all. That day will come. Until then, we dream. Good night. And so, we come to the end of our journey. But before we part, let us take one last look at this world that has captured our imagination. Imagine yourself floating in space, far above Iapetus. You are suspended in the void, surrounded by stars. Below you, the moon rotates slowly, taking nearly 80 days to complete a single turn. From this vantage point, you can see both hemispheres at once. On one side, the bright ice of Roncevaux, Terra, and Saragossa. Terra gleams in the faint sunlight. On the other side, the dark expanse of Cassini Reggio absorbs the light, appearing almost black against the starfield. And there, running along the boundary between light and dark, is the ridge. From space, it appears as a thin raised line, barely visible unless you know where to look. But as you descend closer, its true scale becomes apparent. The mountains grow larger. Individual peaks become visible. The shadows lengthen, revealing the steepness of the slopes. What seemed like a subtle feature from orbit becomes a towering wall from up close. You descend further. The surface rushes up to meet you. You can see craters now, scattered across the ice. You can see the texture of the ground, rough and uneven, marked by billions of years of history. And then you are standing on the surface, at the base of the ridge. The wall rises before you, impossibly high. You cannot see the top from where you stand. The slopes stretch upward, vanishing into the black sky. The scale is difficult to comprehend. You begin to walk. Your footsteps leave prints in the ice, the first marks of a visitor from Earth. The surface crunches beneath your boots, hard as stone in the bitter cold. As you walk, you notice the details of the terrain. Small ridges and valleys, the imprints of ancient impacts, boulders scattered across the ground, tumbled down from the heights above. The texture of the ice, crystalline and fractured, catching the dim sunlight and scattering it in unexpected directions. The silence is absolute. There is no air to carry sound. Your own breathing is the only thing you hear, amplified inside your helmet. The loneliness of this place presses in on you, vast and indifferent. But you are not alone. Behind you, somewhere among the stars, is Earth. Billions of people going about their lives, unaware of your journey, and yet connected to you through the chain of exploration that brought you here. You think about the scientists who first saw the ridge in the images from Cassini, the wonder they must have felt, the questions that flooded their minds. How did this form? What does it mean? What can it tell us about the history of this moon and the solar system that contains it? You think about the engineers who built the spacecraft that carried those cameras, the years of work, the careful planning, the moments of triumph and despair, the launch that sent the probe on its 7-year journey across the solar system, the arrival at Saturn, the first images of the rings and moons, the growing excitement as discovery followed discovery. You think about the dreamers who imagined such journeys long before they were possible, the writers and artists who depicted voyages to other worlds, inspiring generations of scientists and explorers, the visionaries who believed that humanity could reach the stars, even when such beliefs seem foolish. All of them are with you now, in spirit, if not in body. All of them contributed to this moment, this footprint on the ice of Iapetus. You continue walking, approaching the base of the ridge. The slope rises before you, steep but not impossible. With the right equipment, you could climb it. With enough time and determination, you could reach the summit. But not today. Today, it is enough to stand here and look, to witness, to appreciate. The ridge is ancient beyond comprehension. It has been here since before the first life appeared on Earth. It has watched as our planet evolved from a ball of molten rock to a world of oceans and continents. It has been here through the rise and fall of the dinosaurs, the emergence of mammals, the long, slow development of human civilization. And it will be here long after you are gone, long after everyone you know is gone, long after the languages we speak have been forgotten, and the nations we build have crumbled to dust. The ridge is a reminder of our smallness, but also of our greatness. Small creatures that we are, we have reached across space to see this place. We have understood, at least in part, how it came to be. We have added our knowledge to the great tapestry of human understanding. That is no small thing. You take one last look at the ridge, fixing the image in your memory. The steep slopes, the sharp peaks, the shadows stretching across the ice, the black sky above filled with more stars than you could count in a lifetime. And then you turn and begin the long journey home. Behind you, the ridge stands silent, patient, eternal. It will be here when we return. And we will return, perhaps not in your lifetime, perhaps not for many generations, but someday humans will walk on the surface of Iapetus. They will climb the slopes of the ridge. They will stand on its summit and look out at a landscape that no human eyes have ever seen before. And they will think about you, about all of us who wondered and dreamed and worked to make such journeys possible. They will carry our legacy with them, just as we carry the legacy of those who came before. This is how exploration works. Each generation builds on the achievements of the last. Each step forward opens the door to new steps. The journey is never finished because there is always more to see, more to learn, more to understand. The ridge on Iapetus is one stop on that endless journey. A waypoint in our exploration of the cosmos, a place where we have paused to wonder before continuing on. And what a wonderful place to pause. So as you drift off to sleep tonight, carry the image of the ridge with you. Let it remind you of the vastness of the universe and the persistence of the human spirit. Let it inspire you to keep asking questions, keep seeking answers, keep reaching for the stars. The mysteries of the cosmos are gifts. They give our lives meaning. They give us something to strive for. They connect us to generations past and future, all united in the great project of understanding. The ridge on Iapetus is one such mystery, partly solved, partly still hidden. A puzzle that has engaged some of the best minds of our time. A challenge that will continue to inspire for years to come. Embrace that mystery. Let it fill you with wonder. And know that by wondering, you are participating in something beautiful. The universe created us. And now we are learning to understand the universe. This is the cosmic cycle coming full circle. Matter becoming aware of itself. The universe contemplating its own nature. You are part of that contemplation. Every thought you have about the stars, every question you ask about distant moons, is the universe thinking about itself through you. This is the deep meaning of exploration. Not just to collect data or take photographs, but to participate in the ongoing process of cosmic self-understanding. To add your thread to the tapestry of knowledge that humanity is weaving across the ages. The ridge on Iapetus is one thread in that tapestry, and by learning about it, you have added your own threads, connecting your thoughts to the thoughts of scientists and dreamers around the world. Sleep now. Let your mind rest from the long journey we have taken together, but keep the wonder alive. Keep the curiosity burning. Keep asking the questions that have driven humanity forward since we first looked up at the sky and wondered what those points of light might be. They are suns, other worlds, places of mystery and beauty beyond imagination, and someday we will visit them all. Good night, traveler. Sweet dreams. The ridge on Iapetus will be there when you wake, standing tall, keeping its secrets, for now. And remember, in the quiet of the night, when the world grows still and the stars shine bright through your window, the same light that touches your face has traveled across the vastness of space. Some of it has bounced off Saturn's rings. Some has reflected from the surface of Iapetus. You are bathed in the light of distant worlds, We are all connected. Every atom in your body was once part of a star. Every breath you take contains molecules that have circled the globe. The boundaries we draw between ourselves and the universe are illusions. We are part of it. It is part of us. The ridge on Iapetus is not separate from you. It is made of the same stuff you are made of. It follows the same laws. It exists in the same cosmos. In some strange way, when you think about the ridge, you are the universe contemplating itself. Let that thought carry you into dreams. The night is deep, the stars are watching, and somewhere far away, the impossible wall of Iapetus stands silent beneath the infinite sky, waiting, always waiting, for us. Good night, rest well, dream of stars and moons and walls that rise to meet the sky. The cosmos awaits your return, until we meet again among the stars. Sleep peacefully tonight. The journey continues in your dreams. Sweet cosmic dreams await you now. Good night. Rest.